let's do part A. Part A, where do you start? Start with an n, right? You'll always start with the principal quantum number because it dictates the rest of your numbers. So, if n is equal to 3, you ask yourself, what are the allowed values for the orbital angular momentum quantum number L? So, what values of L can we have if n is 3? 2. Also what? Don't just give me one of them, give me all of them. 0, 1, and 2, right? You always start at 0 and you add 1. There's a minimum value, always 0, up to a maximum value. So these are all the allowed values you could have if you were to do physics with them, right? And describe some basic principles of angular momentum. So are we good so far? Or are we in trouble? We're in trouble. Because it's asking us, is L equal 3 okay? But that's outside of the bounds. It's outside of the maximum value that our L quantum number can have. So long story short, as Mohammed kind of hinted at this, your L cannot be the same value as n, right? Remember, the upper limit is n minus 1. So you always have to have a cap at n minus 1. Yeah? So it's not allowed simply because your L cannot be the same value as n. What about NL negative 2? Is that okay? Or no? What are the rules for ML generally, if you know what L is? What range of values can magnetic quantum number have? Negative L to positive L, right? So you can have negative 2 to positive 2. So you start at negative 2, so you have negative 2, negative 1, 0, positive 1, and positive 2. And so notice negative 2 is within that boundary. It's within those allowed values. And so there's no violation there for your magnetic orbital number. So that one's okay. The problem is only due to our L quantum number, right? So far so good? Not too bad? Kind of a warm up? Here's the one that might get you requiring to think a little bit more. But here's a strategy. Here's a tip. No, Mohammed, you got a tip. Oh, you want to take a guess? Okay, what'd you say?
50.
50. What'd you come up with over here?
5 to the 5th power.
5 to the 5th power. What number is that, bro? Simplify.
Oh, that's
Way too many. It's a good attempt. Your first attempt was actually pretty good too, and you're very close because 25 and 50 is off by a factor of 2.
Oh.
And 2 is related to the spin. So one of you is right. So much is which one? Well, let's tabulate. Yes? 50. So here's a tip, okay? Instead of counting all the possible states, what you can do is, as a time saver, count up the number of ML states first, right? And then you know for every ML state, there's a spin up and a spin down. So you figure out the total number of ML states, and then you just double it, yeah? So hint, Mohammed is a little bit closer, because 25 times 2 is the 50. So let's keep track. Yes, let's start. You know that when n is equal to 5, the allowed values for the L quantum number range from 0 to 4. You got to do each one separately. So for the first one, easy, right? When L is 0, you know that ML can be from negative L to positive L, which means the only value that magnetic quantum number can have is 0. Yeah. So if you were to add up the total possible ML values, it's a total of just simply one value, one number. Easy. Do the next one. When L is equal to 1, your magnetic quantum numbers range from negative 1 to positive 1. Yeah, don't forget about the 0. So if you were to count them up, how many total magnetic numbers do you have? Nope, just MLs. Count them up. You just have the 3 numbers, right? Remember, I'm going to use a trick because of symmetry. I'm going to add them all up, and then multiply by 2 in the end to take into consideration the spin. P.S. I hope you're remembering the shortcut I gave you last time, because there's a quick formula to figure out how many ML states there are in relation to the L quantum number. What was the formula? Do you remember? 2L plus 1. So you can use that to save you some time if you like, right? 2L plus 1 over here, 2 times 0 just gives you the 1. 2L plus 1 over here gives you the 3. Now you don't have to start labeling them unless you really want to. You can use that shortcut. If you were to do it the long way though, for L equals 2, you get, of course, 5 values, right? From negative 2 to positive 2. Again, use the 2L plus 1 as a shortcut to verify your answer. 2 times 2 is 4 plus 1 is 5. We're almost there. We've got 2 more to do. So for L equals 3, the magnetic quantum number goes from -3 to +3. You count them all up, or you use the 2L plus 1. 2 times 3 is 6 plus 1. You get the 7. And last but not least, you can see why it's looking crazy, because you have a lot more digits to keep track of. That's why I use these shortcut formulas. You get 9. Now we haven't answered the question yet. We've just been tabulating and setting up everything. If you wanted to answer the question, you would have to add up all of the ML states, all of the magnetic quantum numbers, and then you have to multiply by 2 in order to take the spin into consideration, because there's always spin up or spin down, positive half or negative half. So you can use some simple algebra here, right? 9 plus 1 is 10, and 3 plus 7 is another 10, so you're at 20. The only thing left over is 25. So David was correct. There are 25 NL states, but if you wanted to include the spin, that's why you got to multiply by 2. So great job, Mohammed. 50 is the correct answer here. You know I'm a fan of shortcuts, right? There's actually a formula you could use to, instead of having to do all of this chunk, just come up with a really quick formula to predict it. Here it is. I'll let you think about it and see why it works, but it just works. All you do is figure out what your n is, your principal quantum number, is square it, which I think is what David did, because you remember something related to squares, right? And then you have to multiply by 2, don't forget, for that spin effect, yeah? Notice it works, because, well, let's go back over here. For this problem, we did n equals 2, right? So apply 2n squared. So what's 2 squared? 4 times 2, you get 8. The total number of electrons you can fit is 2 plus 6. We said 8 earlier, right? So it works very nicely, and instead of having to come up with this serial killer tree-looking list like who done it, you can just quickly apply the formula. It might not seem like a big deal, but you're going to see this in use later for the problem that we're going to solve on the exam, so please don't forget to include it on your equation sheet, especially for the question that we work on. How we doing? What questions do you have about this particular problem, counting the total number of quantum states? Seems like we're good so far. Okay. So what have we talked about so far? We've talked about the different possible values that N, L, ML, and MS can have. But we haven't talked about the specific ordering of which electrons go where, if you're talking about the hydrogen atom or even a more complicated atom. Turns out what I'm referring to is the electron configuration. The electron configuration tells you, according to the Pauli exclusion principle and Hund's rule, there's lots of chemistry rules that tell you how to do this, but it tells you the order in which electrons will be placed in a particular quantum state when you add them to an atom, for example. So what you need to know, in general, electrons will be placed in atoms with increasing available energy levels. So when you first put an electron in, it's going to have a relatively low amount of energy. And when you add more electrons, or if you move up in the states, in the orbits, in subshells, it's going to have more energy associated with that. There's a lot of different tricks you can use to memorize the electron configuration. I hope you will utilize this one for one of the questions you will also find on the exam. I'm going to ask you to write down an electron configuration, but I've given you a nice little cheat sheet here to help you out. On your piece of paper, what do? You write numbers 1 through 7, or you can even go farther if you want. Okay? These 1, 2, 3, 4, 5, 6, 7s are in reference to n, your principal quantum number. And then what you're going to do is for every single row, you're going to start labeling S, and then in the next row, you keep the S, but you add the next letter, you add the next subshell. So it's going to be P, yeah? You can see the second row has SP, yeah? For the next one, you're going to start with S, and then do P, and D, etc. For every row, you keep adding a subshell. Does that make sense? I have not listed, but you could have technically written down G here, for the next subshell, right? It's alphabetical after F. You can have G here, and then GH here for the sixth one, and GHI if you were really crazy for the last one. It just continues to extend generally in that way. Once you have your little table built, how do you read it? You read it diagonally, which is where the blue arrows are pointed. So you start labeling and throwing electrons in your atoms in the 1s state, right? So the very first thing you're going to write down, 1s. What you have to remember, though, is how many electrons will fit in that subshell. But we talked about that earlier, right? How do you figure out how many electrons are going to fit in a subshell? What do? Let's say you forget that it's supposed to be 1s2. How do you remember what the 2 is? How do we get to 2 in the first place? Oh my god, I remember that chart. I see it on the left side. It was 2. How do we get to 2? You count the number of ml states, and then you double it, right? So how many ml states are there when L equals 0? How many NL states? There's 1, just 0, right? ML is negative L to positive L. It's 0, so it's just 0. So you can count the number up. There's 1, and then you double it. There's 2. That's why we ended up with the 2 here, yeah? You can do the same exact trick for all of the other ones. So whenever you see a P, that means L is equal to what? SPDF. S is 0, P is 1. From that, you can use the shortcut. The number of mLs is 2L plus 1. So 2 times 1 is 2. Plus 1, there are 3 mL states. And then you double it for the spin. So whenever you see a P, you're going to have a 6. You can do the exact same thing for your Ds or even your Fs. It follows the same pattern. That's how you know what number to put maximum in the superscripts. But the ordering goes by the blue arrows that you see in your chart over here. So you start at 1s, and then the next thing is 2s, next thing is 2p, and then 3s, and then you have 3p, 4s. I hope you can see that I'm just reading this off, but I'm following the chart to get that, right? I followed the chart to write this part down for you. Yeah? And then you just keep on going until you've filled in however many electrons you're dealing with. So for example, let's say I asked you to write down the electron configuration of hydrogen. Yeah? Hydrogen is which one on the periodic table? Which number on the periodic table? Uno, right? The first one, yeah? So that means in order for it to be neutral, an atom, it has to have 1 electron. That means that its electron configuration is just going to be labeled as 1s. Or if you want to be super specific, it'd be 1s1, right? The 1 referring to how many electrons are in that subshell. Yeah. If you wanted to write down the electron configuration of helium, which is number 2 on the periodic table, that means you need 2 electrons, right? That means you're going to write down 1s2, because you can fit 2 total electrons in that S subshell. What happens if you go to the next one? Let's say you go to lithium. Lithium is number 3, atomic number 3 on the periodic table. Now remember, only 2 electrons can fit in a 1s shell. That's what the 2 means, the maximum capacity. No more spots available, right? Tickets are all sold out. That means that 3rd electron has to go to the next subshell. Yeah? In this case, it's going to go into the 2s subshell. Yeah? It's a different n value. It's some distance further away from the nucleus, but it's also still angular momentum is equal to 0. No angular momentum. I guess I should say no quantum number angular momentum. So for lithium, it would be what? 1s2 and then 2s1, right? Because you only have 1 electron to count for the full of 3. So long story short, whatever atom you have, you can double check to make sure you have the right number of electrons. Because all you got to do is add up all the superscripts, yeah? The total number of all the superscripts added up better be the same number of electrons that are inside of your atom. Yeah? Placing electrons in a particular order, particular sequence, inside of your atom. Like a lot of things in life, this is a general way to do it. Not all atoms follow the exact same conditions because things are a lot more complicated, especially when you're dealing with your transitional metals, the big boys in the middle here of your periodic table. Yeah. So they follow slightly odder rules, but if you're ever asked this on your homework or an exam, I want you to follow the pattern I'm giving you here instead. Okay? Speaking of the periodic table, I might make a couple of comments here because, well, back in the 1800s, they knew of a whole bunch of these elements, but they didn't know how to organize them. It's like, do you organize them by mass? Do you organize them by electrons? Do you organize them by the shape, right? The size? How do you organize all of this stuff? There's a lot of stuff you have to figure out. But now we currently organize them by what we just described earlier, which is the ordering of the electrons inside of your atom. I hope you can see that the first row, you can look at that periodic table if you want as well, the first row only has 2 elements. I know on mine I have 3, but it's duplicated because hydrogen can sometimes be classified as a metal or it can be classified as a gas, depending on circumstances. But technically there are only 2 elements, 2 atoms in the first row. How come? Because it corresponds to n equals 1. When n is equal to 1, use the equation I gave you earlier, 2n squared. What are the total number of states that you can have when n is equal to 1? 1 squared times 2, which is 2. That's why your first row, that's why the first row has 1s out front, because it's corresponding to the first shell, yeah? If n is equal to 2, what's the total number of electrons you can shove in that shell? 2n squared. So n is 2, so 2 squared is 4, double the 4, you get 8. Did you ever count the number of elements in the second row? 1, 2, 3, 4, 5, 6, 7, and 8, right? Because all of those atoms have electrons that can fit in that second shell. Now notice, be careful, shell means both subshells, right? Because you can see on the left side, you have the 2 S's, and on the right side, you have the 2 P's. Remember, S is one subshell, P is a different subshell. But if you had all the total electrons from all the different subshells, you get the total number of electrons in that shell, which was 8. Yeah? If n was equal to 3, how many total electrons can you shove in that particular shell? 3 squared is 9 times 2, right? 18 total electrons you can shove in that shell. I want you to pay attention to the 3's that you see on the table. You got 2 over here, yeah? You've also got 6 over here for a total of 8. That means you're missing 10, yes? For a total of 18. Count these over here. These are your transitional metals, and they have 3's in them, yes? How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. There's a total of 18 elements, right? Because you can have 18 total maximum electrons in that whole shell. And remember, the shell is being subdivided into 3 different subshells because you got the 3s, you got the 3p, and you got the 3d. Yeah? You can keep having fun with this, right? If you want to go to sleep at night, figure out how many electrons you can shove in the 4th shell. That one's easy, right? Because it's 32. That means you better count 32 of those electrons, or that means you can have 32 atoms with different configurations of electrons. Yeah? Not only is the periodic table organized by how many electrons you can fit by row, but it turns out if you read them vertically, if you look at the columns, they all suggest they have similar chemical properties. That means all the things in this first group will behave similarly when you mix them in some kind of chemical reaction. How come? Because the very first column means that you only have 1 electron in that particular subshell. And if they all have the same number of electrons in the outer edge, they're going to behave very similarly when you combine them with something else chemically. You might be most familiar with the last column, which is the noble gases or inert gases. They're very famous because they're their shells are all full, right? They are very unlikely to give up an electron or to take in an electron because their orbitals are, so to speak, happy or fulfilled. Yeah? So the periodic table is very nicely organized because there's a reason there's a certain number of atoms in a row, and there's a reason there's a certain number of atoms in a column, because it's going to predict the chemical behavior. This is why back in the day when Mendeleev was trying to come up with this periodic table and figure out how to organize them, he noticed there were tons of gaps. There were things they didn't ever notice or observe experimentally, and of course, fast forward about 20 years, all of those elements were found, right? Because he had placeholders of what to find and where to expect it, and what kinds of chemical behaviors they should follow. So this means that if you want to predict the next biggest element past number 118, you would know similarly how they would behave chemically if you were to mix them in reaction. This is very challenging, however, because as we will discuss a little bit later in the nuclear physics section of this course, all of these have an extraordinarily small lifetime. They live for a very, very short amount of time. I'm talking nanoseconds, picoseconds. So how do you do chemical reactions with something that lives only for nanoseconds or picoseconds? It's a challenge, right? But regardless, those atoms have similar chemical behaviors because that's where they're placed on the periodic table. So it's kind of fun to think about how the periodic table is organized and relating it back to maybe something you recall from chemistry, and we're putting it all together because everything comes from where? The Schrödinger equation, yeah? That's a physics thing. Don't let those chemist professors tell you otherwise. All right, good. Okay, I have two last things I want to talk about for this chapter. One brief comment, and then the second thing you'll need to know about to help you solve the practice problems that we'll do in a moment. If you think critically about the information I've given you so far, if you've thought really long and hard about the consequences of electrons changing from one orbital to another orbital, there's some funny stuff that goes on. Okay? Here's a graph. It's a picture of the hydrogen atom and the transitions an electron could undergo in a particular hydrogen atom. So for example, you can see that for an electron in a hydrogen atom, if it's located within n=3 orbit, it's in the third shell, yeah? If it gets demoted, if it moves down and transitions to the second shell, what actually happens is its angular momentum quantum number changes. I'm going to say that one more time, because that should be a huge red flag to you. When you go from n=3 to n=2, when we talk about transitions all the time, what actually happens is the angular momentum quantum number will change. Think about it for a second. The rules for L are governed by n, right? If you have a specific n value, your L values go from 0 up to n-1. So if n changes, L must change as a result, which kind of makes sense, right? You don't think there's anything sus going on here. However, if you think a little bit harder than that, there's kind of a huge implication here. You know that when an electron moves from one orbital to another orbital, or from one shell to another shell, it emits a photon. Yeah, poof, a piece of light pops out. Yeah, electromagnetic radiation. But what happened to your angular momentum? Do you remember the L that I started the class with? L was h bar times the square root of L times L plus 1. It was a formula to calculate the total angular momentum, orbital angular momentum. When you go from n=3 to n=2, your angular momentum of the system changes, right? Of the atom, it changes. It goes from one number to another number as a result of moving between L=2 to L=1. Might not seem like a big deal, but if you think about it some more, you're like, wait a minute, my L is related to the angular momentum. And if you're a good physics student, you might remember from physics B4A that, angular momentum is conserved. Just like linear momentum is conserved. Just like energy is conserved. So there's a big problem here because we're saying that when an electron jumps down in orbit, it's changing its total angular momentum. So that would be a violation of classical physics, right? Even quantum physics, like, okay, whatever, but you're breaking classical physics here with that suggestion. This is the implication. We do not believe that angular momentum should not be conserved. It should always be conserved. You shouldn't be able to violate any conservation laws that have already been set in stone. So the suggestion here is that while the angular momentum changes as the electron transitions downward, the photon that gets kicked out carries angular momentum with it. And that's how you can argue that angular momentum as a whole is still conserved. Now that might seem like a crazy, crazy bold idea, and in fact, it is kind of crazy if you think about it. But it kind of does make a little sense too, because you've seen earlier this semester that the photon has an energy associated with it, right? E equals hc over lambda. We've used it 100 times probably by now. And I told you, I said, trust me, bro, that Einstein claims in his original paper that photons also have a p, they have a linear momentum. P is equal to E over C. So if a photon has energy and it's got linear momentum, it's not that far of a stretch, right, to say that it should also have some kind of angular momentum as well associated with it. Which is kind of hard, because you're like, okay, bro, how do I visualize that? Okay. And here's one way you can conceptualize this. Now remember, don't take this literally, just like the spin of an electron, you should not take literally, that is not correct, but it has an intrinsic property called spin that helps you visualize that. But the way that you can conceptualize the angular momentum of a photon is as it's moving in a helix, moving from point A to point B. You know a photon has E field and B field, right? And you just assume that it just moved in a straight line. But I want you to imagine that it's kind of revolving like this as a helix as it's moving from point A to point B. If you do that, you can, hand-wavingly say, okay, well, we're looking at like rotational motion, there must be an angular momentum associated with it. That's one way you can visualize why maybe a photon could potentially have angular momentum as a result of our discussion in the transitions here. It's just an interesting side note, yeah? I'm not going to ask you anything about that, but it is an interesting property, and it actually tells us how things become polarized in certain directions, and what kinds of angles of light get emitted from a particular atom. There's different angles that you can get based on analyzing the polarization and the transitions here for angular momentum. Last thing for atomic physics. We've got a lot to talk about in this topic, right? And I've kind of handpicked certain things that I want to focus on the most. But this one is interesting because we have talked about it in 2 different lectures for atomic physics, so it must be important, right? We saw Bohr predicted the energy levels of a hydrogen atom. And you could tweak that in order to talk about hydrogen-like atoms. The only requirement is you had to have 1 electron in the entire atom, right? And if you did, you could still apply that equation. But obviously that was not completely correct, because we said it only works for a very small subset of atoms or elements. I told you earlier that quantum mechanics works for all of those atoms. As long as you can identify your N, L, ML, and MS quantum numbers, it accurately describes all the physics you need to know about the more complex ones. Turns out Bohr was not actually really off. He was actually very close. You can talk about bigger atoms, more complex atoms, multi-electron atoms is what your textbook calls them. You can talk about them, but you have to make a small tweak to the formula. Okay? So if you want to analyze transitions of electrons in multi-electron atoms, say for a metal, yeah, you have tons of electrons inside, and you want to know what the energy levels are for every different N, every different orbit, it turns out you use exactly the same formula, but the tweak is you no longer just use Z as the atomic number. We have to modify it. In other words, we have to calculate the effective EFF atomic number. The way that you calculate your effective atomic number is, I've given you the formula here, You take the atomic number, you figure out how many protons are inside of that nucleus, right? Positive charge. But we have to count and subtract the number of electrons that are shielding that electron. Here's the problem. Imagine for a second, you have a nucleus that's positively charged, and you have 2 electrons here that orbit around in an n=1 shell. Yeah? Your job might be, hey, tell me what the energy of the n=2 electrons have, right? If you want to know the energy of the electrons in n=2, it's no longer simple because you have interactions of electrons with other electrons. That's the problem with Bohr's model. So you have this electron that is actually being shielded from the 2 electrons that are closer to the nucleus. This electron in the n=2 shell is not experiencing the same full net charge as the ones closest to the nucleus. These 2 electrons are in the way. They're shielding. They're like white knights or something, right? They're shielding the nucleus from the electrons on the outer edge. So what you have to do is count the number of electrons that are shielding the nucleus, because that's the effective atomic number that those electrons are going to experience that you're evaluating the energy level of.
So if we have multiple electrons on orbit, are you gonna count all the electrons?
So you don't count those electrons, you count the electrons below them. So only the electrons below the orbital that you're trying to calculate the energy level for. So if you have 2 electrons here, yeah? Remember, that's the only amount you can fit, right? When n=1, you can only fit 2 electrons. If I want to know the energy level of an electron in n=2, the number of shielding electrons is how many? 1 plus 2. I have 2 electrons here, yeah? So I don't count the electrons in the n=2 orbit because those are not shielding, yeah, the nucleus. The only ones that are shielding it are the electrons closer in the n=1 orbit of that electron. Atom. Make sense?
Yeah.
Okay. So this is what you need to know in order to answer the question. Ready for a practice problem? Okay. I'm going to show you how to do this once, and then I'll do the other one. Yeah. You got a question, Nick?
I don't know if this is going to help.
Okay, yeah. Always look at the practice problem helps first, right? Okay, here we go. You take a beam of electrons and you shoot it at a metal, bismuth in this case. Bismuth, you're told, has an atomic number of 83. That means, remember, it has 83 protons in it, and if it's neutral, it's got 83 electrons. Yeah. What happens when you shoot the electrons at the metal? It tells you that 1 electron in the second orbit, the second shell, n=2, gets kicked out, gets ejected. Remember, an electron smacked into another electron will kick it out of the shell. What that means is you have a hole, you have a vacancy now, and what occurs is an electron from a higher shell, from n=4, is going to drop down and fill in the hole. It's just what we say from the physics term, fills the hole. So we have an electron, they got kicked out of the second shell. An electron from the 4th shell is going to fall down and transition and enter that second shell. The question becomes, tell me what the wavelength of that photon is as a result of going from the 4th shell to the second shell. Yeah, what is the wavelength that gets ejected as a result of this transition? I hope you would agree that you cannot use your hydrogen atom equation here. You cannot use your hydrogen-like atom equation here. You must use the multi-electron atom equation I just showed you on the previous slide. What it means for you is all you got to do is figure out what the effective atomic number is ZF, right? And if you do that, you shove it in the equation, you're good to go. So here's what you have to do. You need to plan ahead a little bit. Do you remember the trick I gave you earlier, which is based on your n value, you can use 2n² in order to determine the total number of electrons that are allowed in that shell. Yeah? So what I'm doing is I'm figuring out right here how many total electrons can I shove in that shell when n=1, when n=2, when n=3, and when n=4. I'm applying the shortcut I gave you earlier, 2n², so you got 2, 8, 18, and 32. With me so far, this is just prep work. This is just knowing how many electrons maximum you're supposed to have in the shell. Here's where we have to do physics, because in the physics problem, I need to know how many electrons are shielding, yeah, the orbit, the shell that I want to calculate the energy level for. So what do? You imagine, yes, that in the initial state, in the n equals 4 state, right, the fourth shell, you have to count the total number of electrons that are below that. So how many total electrons are there in the third shell, second shell, and the first shell? You just add them up. Those are the total number of electrons that are shielding these electrons to figure out the energy levels. So that's why you made this list, because you now know the total number of electrons that exist. However, be careful. One electron was kicked out, yes? The electron here disappeared. There's a vacancy. So how many total electrons do you have if you add 2, 7, and 18? 18 plus 7 is 25. 25 plus 2 is 27, yes? So that would be the total number of electrons that are going to shield that n equals 4 shell, the electrons in that fourth orbit. So I know now how to calculate my effective atomic numbers. You take Z, that was 83 bismuth, subtract the total number of electrons that were shielding that fourth shell, and then you just plug it into the equation that you're familiar with, 13.606 negative, yeah, divided by n squared. Now notice your n here was 4. That's where it started, right? It's the initial energy state of the electron. You're going to do the same thing, but now for the electron when it transitions down to n equals 2. So, you have an electron go from 4, and now it filled the hole. It's in n equals 2. So now, you need to figure out the energy level of the atom in n equals 2 shell. So you have to ask yourself, how many electrons are below the n equals 2 shell? So what do you think? How many electrons are in the below the n equals 2 shell? Just 2, right? 2 that are orbiting really close to the nucleus. That's why the number of shielded electrons in the final energy state is 2. So you're going to do Z minus the 2 shielding electrons, and then that'll give you your effective atomic number. Why does this help? Because I think you remember by now we solved several of these problems that the difference in energy levels is equal to the energy of the photon that gets kicked out, right? So what you need to do now is take the initial energy level and subtract the final energy level, yeah? And that subtraction in energy levels better be the exact same energy as your photon, right? Your gamma. I'll let you go through and crunch out with your calculator. You can just trust me for right now, but you should end up with almost 20 keV, 20,000 electron volts as the energy of your photon. And then you do the same trick that we've done before. The question's not asking about the energy, the question's asking for the wavelength, yeah? So make sure you convert it by using your HC over lambda equation, and then making the appropriate conversions to SI units as necessary. And you're really careful with your units here. Your energy is in EVs, so you've got to convert to joules. And if you think really, really hard, all of this stuff is going to end up giving you meters. But the question is asking you, please, calculate the wavelength in nanometers, yeah? So don't forget to convert into meters. So very small wavelength, only 0.06 nanometers. The problem does tell you this is an X-ray, so it's not too surprising. X-rays have very small, short wavelengths. I'm thinking what Nick is going to ask me. When do you use this for? What's the application, right? Sometimes that's important. But I hope you can imagine that if you take a beam of electrons and you shoot it into metal, you can predict what kinds of wavelengths you're going to generate. Let's say you have a very specific experiment you're trying to do, and you need photons or X-rays of a very specific energy or a very specific wavelength. Now you can figure out exactly what the photon's wavelength is, or figure out the transitions, and then isolate those photons to do an experiment with. I'm teaching you how to make X-rays here, right? You shoot electrons at bismuth, a metal, and boom. You
Is that how it's actually done?
Yeah.
Like in doctor's office?
How do you think X-rays are produced?
I don't know.
Magic.
Magic, physics magic. This is not the only mechanism to generate light, right?
What-
We need to accelerate charges.
What happened to the neutron in all this?
So we haven't talked about neutrons yet.
Okay.
For all you care about, nothing happens to the neutrons.
We haven't discovered that yet?
We haven't discovered it yet. Yes, when we get to nuclear physics, we will discover that. Yes. But essentially, the only thing that matters here for atomic physics is the protons and your electrons. How we doing? What questions you got on this one? Do you understand the shielding electrons a little bit better now? Count the number of electrons below that shell. That's all you got to do, and then throw it in your equations. Ready to talk about the problem that you're going to see on your exam?
Yes.
Similar to it? Okay, here you go. It's very similar, except it's slightly different, obviously. We're going to do the same thing. Take an electron beam, shoot it at a something. We don't know what it is. It's unknown. It's an unknown metal. What's going to happen is an electron from n=1 shell is getting kicked out. Poof, yeah? That means that there's a hole, there's a vacancy, there's an opening. You're told that an electron from the second shell is going to drop down and transition to that first shell. It's going to fill the vacancy. It tells you what the wavelength of that photon is as a result of that transition. Yeah? About 0.1 nanometers. The question is, what is the atomic number? What is the thing on the periodic table that you shot the electrons at? Which is very practical, right? You could do this in the lab. You take electrons, you measure the photon's wavelength, and you go, yeah, I guess it must have been this metal I was using, right? Kind of reverse engineering it. Would you agree that you would do the same process to solve this problem? It's a conservation of energy statement, yes? That is, the energy of your photon that gets kicked out is the difference in energy levels from where it started to where it ended. Now be very careful. In other physics classes, you're getting used to the fact of doing a change in something, a final minus initial. Be very careful. That's not how atomic physics works. The energy of the photon is always, because you're going from a high energy level, like n=2, down to a low energy level, n=1. It's always where does it start minus where did it end for atomic physics. If you do it the other way, you get a negative photon energy, which is really bad. You don't have negative energies of photons. So what are you going to do? You're going to need to figure out what your shielding effect is, yes? So I want you to think about this for a second. The electron in the second shell, how many total electrons are below the n=2 shell?
N=what?
Okay, so we're looking at n=2, right? How many electrons are below that shell that are shielding? Now remember, one got kicked out, right? You had total 2 in the first shell, but one of them got kicked out. So how many electrons you got now? 1. There's only one shielding electron when you're looking at the second shell. Yeah? So Z-1 would be how you calculate the effective atomic number. If you were to ask, hey, how many shielding electrons do you have in the first shell? You ask yourself, how many electrons are below that are shielding the nucleus? There's 0. There are none, because that electron that's in the n=1 shell is the closest to the nucleus. There is no shielding effect, in other words, for that electron in the first shell. So that's why on the right side, for my final state, I have Z-0, 0 shielding effect. With me so far, I'm setting up my equation, but you can see I'm getting into a pickle, yeah? I got a Z over here, oof, and I got a Z over here, and oof, they're both square. We could do it, but hopefully you're seeing where the problem is going to come up eventually. A brief reminder, I think you know how to calculate the energy of the photon, yes? You're given the wavelength already, so can't you just use hc over lambda? Yeah, convert everything over. I'm not going to bore you to tears. I won't show you that. Okay. Take a look at my work. Some students get confused by this. Okay. Take a look at what I've done. it's a negative energy level minus a negative energy level. So just like we did before, I'm going to move my positive thing to the left side and my negative thing to the right side. We're going to swap terms. I hope you can see that this thing now becomes positive because the minus and the negative sign. So then my z squared term comes to the left. And on the right side, my z minus 1 over 2 squared, 4, is going to be on the right side. Yeah? Notice I'm going to simplify this a little bit because my 13.6 EVs is in common with both of them, so factor those out. Yeah? Again, I'm not going to show you how to calculate the energy of your photon. It's in the PowerPoint if you want to go look at it after lecture. But just know that you have to calculate the energy of your photon to know what the left side of that equation is. If you do that, you're left with this statement, yeah? This is the energy of your photon that was kicked out from the transition from 2 to 1. And this was the statement we had when we simplified our difference in energy levels from also 2 down to 1. Your job now is to find Z, right? You're supposed to find Z, the atomic number. Here's my pro tip to you. When you try this and when you get to your exam, get rid of the fractions. Please first, get rid of the fractions. It's going to make life way better. Okay? So what do I mean by that? I mean, because this is my lowest common denominator, I need to multiply by 4 in order to get rid of all of my fractions, all my denominators. So what you do to the right side, you must also do to the left side, yes? Okay. Multiply by 4 over here. You can see what I need to do, yeah? My 4 has to be multiplied by my z squared term. And I've also simplified. I've taken my 13.6 EVs, I've divided them to the left side, and I've also multiplied by 4. Don't forget, multiply by 4 on both sides, yes? Wow, if you stare at this long enough, you're like, ooh, this is starting to look like a quadratic equation. That's where we're headed. So now you should probably put it in the format of a quadratic equation, like ax squared plus bx plus c equals 0. Okay? Simplify, break down, expand, I guess I should say, your squared term. Be very, very careful here with your minus signs. Because as a reminder, you have negative 2z, but then you also have the minus sign out front, which actually makes it a positive 2z. So when you're doing your algebra, just be really, really careful with that minus sign. I think you know how to solve this quadratic equation. You've probably done it a trillion times. Hint, you can use your calculator on the exam to speed things up if you like. Yeah? When you do that, you end up with a number, and you want to choose the closest integer number as the instructions tell you. If you do it correctly, it should be really close to an integer number, just might be slightly rounded. So round to the next number.
So for the 5759, did you round it up or that was just the exact value?
You said this one right here?
Yeah.
So I did this divided by 13.6 and then times it by 4. And then it's only showing the 4 digits then, yes. There's probably more numbers afterwards. So if I asked you, hey, what element is this on the periodic table? All you got to do is you got to figure out where number 30 is on the periodic table, and you're done, right? Which one's number 30? Zinc. So that means you shot electrons at zinc, and that's why, right? Because you witnessed a photon of 0.1 nanometers being released. Pretty cool, right? By the way, it doesn't matter if you take the positive or negative solution. All it does is change this to be positive or negative. And as a reminder, your atomic number always should be a positive number because it's the number of protons. You can have a negative number of protons. Yeah? All right, I'm past time, but I wanted you to see what the problem looked like. Hopefully you understand that. If not, take a look at the lecture notes, make sure you know how to do it, because you'll have a problem just like this one. Maybe different transitions, different photon wavelengths, but the process will be the same. Be careful with the shielding electrons, yeah? Be very careful. Just think how many electrons are below that shell, and you're good. All right, I'm all done yapping. I've kept you a couple minutes late. My apologies. Have a fantastic Halloween, yeah? I'll see you next week on Tuesday. Make sure you get your project stuff done, please, and your homeworks.